Okay, thank you very much for the very nice introduction. It's a great pleasure to be here in this prestigious university and in this prestigious venue to give you an idea about the research that I've been doing actually in the last 10 years. And so this is actually a talk which is thought for non-mathematicians, in principle, at least at the beginning. So the idea is that I want to convey some ideas of our subject to scientists and maybe also to just some people who have some familiarity with certain mathematical concepts. Only towards the very end, I will say something for the experts. I mean, I hope this is going to be fine. Most likely, I will make myself not understandable by the non-experts and boring to the experts, but okay, so that's life. So let's start with telling you what is this Plateau's problem. Like pretty much everything in mathematics, it is not named after the person who really first invented the problem. Actually, the Plateau's problem was first posed by Lagrange. But nonetheless, so there's something very nice that you can do. So take a wire, dip it in a bucket of soap of water, and pull it out. Okay, you will see that the wire spans, I mean, if you do it carefully, yeah? If you do it carefully when you take the wire out of the soap water, you will see that there is a soap film which is attaching to the wire. And this soap film makes interesting shape. So it's fragile, but sufficiently stable. Okay, so the mathematical question that goes under the name of Plateau's problem is, how can we determine the shape of the soap film? So the contribution of Plateau, who was a Belgian physicist working in the 19th century, was to give a very nice and elegant answer to this problem. So if you look at the surface, which is realized by a soap film, you will actually find a surface which minimizes the area among all possible surfaces which span that same wire. Okay? So if you want to be a little bit more precise, actually, that is a local minimizer, not a global minimizer. I mean, that is what the physical principle tells you. If you want to be maybe even more precise, what it really is, it's a stable critical point of the area functional. So that is for the experts and maybe for the physicists who are in the audience. Okay, so therefore you can state what is called the classical Plateau problem, the original Plateau problem. So I give you a wire in the three-dimensional space. A wire in the three-dimensional space is a curve. And I'm looking for a two-dimensional surface which spans this wire and which minimizes the area among all two-dimensional surfaces which span this wire. So this is the original Plateau problem. Now there's a famous saying by Goethe. In German it sounds like this. Die Mathematiker sind eine Art Franzosen, man redet es zu ihnen, sie übersetzen es in ihre Sprache und alsobald ist das Ganze etwas anderes. So, if you translate it, it's the following saying. So the mathematicians are like French. So you talk to them, they translate what you were saying in their own language, and all of a sudden, it's something completely different. So in fact, what we call Plateau's problem in the mathematical literature is the following thing. So instead of being given a curve, which is a one-dimensional object, you are given a general surface, a general m-dimensional surface. So m is the arbitrary dimension. Of course, it cannot be just a completely general surface. So for instance, the wire is what we call a closed surface, right? So you have a wire and it's attaching. I mean, if you just put a piece of metal, like a line of metal inside, you will see you get it outside and there is no soap film, okay? So it's what a mathematician would call an m-dimensional surface which is a boundary, okay? So that's the name for the title of the talk, boundaries. Okay, so you're given an m-dimensional boundary, and you are now not in the three-dimensional space. You are maybe in a very high-dimensional space. I mean, maybe the space has 17 dimensions, say. And it's not even our usual Euclidean space. It's what people actually call a Riemannian manifold. So some ambient geometry, which is not necessarily flat, like our space. And now what you're looking for is a surface of one dimension more. So here you had two-dimensional surfaces. Here you have m plus one dimensional surfaces, which are in your ambient space, which are in some sense spanning your boundary, so they are attached to the boundary, and which minimize the area or the volume, the m plus 1 dimensional area or volume, among all possible surfaces which span that boundary. Okay, so of course one of the things that you could ask is, why? Okay, the two-dimensional problem is physically motivated. It has some interest, some obvious interest. If you're interested in certain type of physics, why are you actually wondering about this very general question? Okay, so let me give you a few answers. So first of all, it is a prototypical problem of what people call calculus of variations. Okay, so in the calculus of variations, you have a certain object, which is called an energy. It assigns a number in a class of objects, and your interest is in the objects which minimize this quantity. Okay, so of course, usually this quantity is called the energy, because you have in mind some system in the natural sciences or some physical system, and the minimizer of the energy actually characterize the stable points of the system, right? So it's physically highly motivated, and it's a prototypical problem because it's very easy to state in geometric languages. So in mathematics, often you take prototypical problems as a starting point for your investigations because you hope to develop techniques to understand the prototypical problem, which will actually be available for much more general problems. So it has a certain mathematical beauty and a certain mathematical elegance, which might make think that if you develop something for this problem, then you can solve many others which are similar. It has actually very many geometrical applications. So again, in mathematics, in geometry, what happens is that area minimizing surfaces, so minimum or solutions of the Plateau problem, they are natural candidates to, for instance, cut more complicated ambient spaces into simpler pieces. I mean, at the point that, this is a remark for mathematicians, of course, at the point that, for instance, if you take the famous resolution of the Thurston's geometrization conjecture for three-dimensional manifolds, there are actually steps that precisely use this idea. I mean, three-dimensional ambient spaces which sometimes are cut into simpler pieces, and you have to think that the surfaces along which you are actually cutting your space are surfaces which minimize the area. So there are some situations in which you do this. Another thing, actually, the fancy high-dimensional version has very surprising connections with modern theoretical physics. So in string theory, there are things which are called Gromov-Witten invariants. There are things which are called D-branes. And actually, Gromov-Witten invariants, for instance, count a certain type of area-minimizing surfaces. In certain manifolds, D-branes are actually area-minimizing surfaces. And they are in very high dimension and codimension. OK, so now, this is another simple geometric example of what I understand by a general ambient manifold and minimizing the area. So here you have a donut, so what mathematicians call a torus. Okay, so actually more precisely, you don't have the donut, but just the outer surface of a donut. Okay, so it's a two-dimensional surface. And imagine that you put actually an elastic wire around this two-dimensional surface, right? So you just stretch an elastic, you think it's a very small elastic. You put it around this surface, and then you let it go, okay? So the elastic will try actually to minimize the length. Of course, it cannot, if the donut is sufficiently solid, it cannot go inside. So the elastic will stabilize among a curve which in a sense minimizes the length among all curves which cannot be shrinked to a point by staying over this surface. So this is an example in which we have a simple situation. So the minimizer is actually one-dimensional, the ambient geometry is two-dimensional, and you see a simple geometric problem in which the minimization problem actually pops out naturally, okay? Now, of course, it's a little bit more difficult to understand what is an ambient three-dimensional space, which is not our usual Euclidean space, and what is a two-dimensional minimizer inside. Okay, that is a bit more difficult to draw. So, of course, if you look at it from the point of view of mathematicians, there are all sorts of questions that you would like to ask at the beginning. So, if you want to solve this problem, what should you understand as a surface? So what is a surface? In particular, what should you consider only surfaces which are nice, they are smooth, they are regular, or should you actually consider also surfaces which have corners? Should you consider surfaces which have cusps or not in your own problem? So this is a very natural question. If you start introducing surfaces which are rough, how rough can you take them? Can you take fractals, for instance? When you have surfaces which are quite general, what does it mean that actually your surface spans your boundary? This is another fundamental question. A third fundamental question is, what is the area of a very general non-regular surface, and how do you compute it? And then there are the typical questions that actually the mathematicians like. So there are these existence questions. So can you prove that there is a minimizer? I mean, often for people in natural sciences, that looks like a weird question. Because often the answer of the mathematician is that there is a minimizer for some reason, and the answer that there is a minimizer is completely irrelevant for finding the minimizer or for having an algorithm which gives you the minimizer. So Hilbert, to his students, used to give the following example. So if you are sitting in a room, there is certainly somebody who has the maximum amount of hair. Because there are just finitely many people. Somebody has the maximum. And so it's an existence theorem which is practically true. It's a typical existence theorem in mathematics, but it's in some sense uninteresting also, right? Of course, there are also the people who have least amount of hair, and they are easier to identify. For instance, here it's very easy to identify. Now, after you have proven, though, what if a minimizer exists, you can ask deeper questions. So what is the shape of the minimizer? And it happens often that actually your existence proof is giving you some insight. What is the shape of a minimizer? One basic question, for instance, is can the minimizer itself have singularities, right? So is it a nice regular surface or is it not? I mean, these are all very deep questions, and mathematicians actually wrote books and tons of papers on them. There is an extensive literature. So let me go very easy on you and just look at a very simple situation. So this is a cartoon picture. So say that you have the easiest situation. So in the easiest situation, you can think that you have a zero-dimensional boundary, so dots. And then you are looking for a one-dimensional object, which is connecting the dots. You are looking for a one-dimensional object which is connecting the dots and which is minimizing the length. Okay, so this sounds very abstract, but you can simply think about the following. So here you have 3 cities, okay? And you want to build a railway. And you want to build a railway which connects the 3 cities and has the minimal length, okay? So this is an example. So this is a minimal railway which is connecting these 3 cities. You also see a motivation for considering a geometry which is different from your usual geometry. So this is something which will be very, very useful if your Earth is completely flat. But Earth is not completely flat. If you have mountains in the middle, probably this is not going to be the best choice anyway, right? Because you have to go up and go down. So you're actually using more length than what you actually see in practice on your own chart, on your own map. Okay, nonetheless, this is an example. And in this example, it's very easy to understand what is your context, what is your framework. So you have dots. You are connecting them with a network. A network, you can think it's just made of straight lines. So all these straight lines have to be all connected together. You cannot have just 2 groups. And what you want to do is want that these straight lines contain these 3 dots and minimize the total length. And that is a framework for solving your problem. Okay, so this framework actually shows you immediately that singularities can occur, right? So here you have a triple junction. So for instance, it's a point where if your train is going through it, it's probably a very good place where to put an intermediate station, okay? So that, for instance, your train can decide to go in one direction or to go in the other direction. So this is the first things that you learn. So singularities are actually likely to occur. That is also a motivation to why you should ask a question like, what is the type of surfaces that you want to consider? Even in this very simple situation, you will see that there are singularities. Now, it's a clear framework, but you have to say that it avoids several challenges. So it's a clear framework that has been used to give solutions to the Plateau problem in very high dimension and codimension. So it's a way that it's a path that you can take even in the higher dimensional case. But there are some things that it does not face. Okay, so of course, the first thing that you see is that it's using polygonal curves. That will not be okay in general. So surfaces, if you're looking at two-dimensional surfaces which span and wire, right, you will immediately realize, if you just make very few experiments, that you will not get polygonal surfaces. You will get actually surfaces which bend. So the higher dimensional case is certainly much more complicated. But not only that, so there are 2 points which are not faced by this framework, and it's the orientation problem and the multiplicity problem. So this can be defined in a very precise way in mathematics, but let me give you a simple example. So let me twist the problem a little bit. So let me say that instead of building a railways, you have the following situation. So you have some factories which are producing some goods here. So these are the factories. And you have some cities where you actually want to distribute the goods. So the dots now, they are slightly different. So for instance, you see that this dot is twice as big as this dot over here. And the reason is that because this factory is producing twice as much goods as this factory over here. Okay, now you are the person owning the factories. You have trucks. You're not using the railway. You have trucks, and you want to send your trucks in such a way that they distribute your goods to the cities. Okay? So let's say that each city is consuming a unit of 1. So you have one consumer, one consumer, one consumer. You have a factory which produces 2, and you have a factory which produces 1. Okay? And now you want to minimize the roads, the amount of road that the trucks are actually going to use. Okay, of course, what you do, well, you do this very simple solution. You take one truck here, and you shoot it to the closest city, right? It would be a very bad idea to send the truck from here to this dot, and the truck from here to that dot. Now what do you do over here? So you use 2 trucks, because you have to reach 2 cities, and you just go directly with one truck to that city, and directly with another truck to the other city. Now, if you had a railway, you would build a railway up to here, and then have an intermediate station, and then distribute 2 other railways in 2 different directions. But now you have trucks. Of course, you can make the trucks go along together for a certain piece of the road, and then bifurcate at a certain point. But that is not effective in terms of costs, because you are moving 2 trucks, and each of them, they are taking a longer road. Okay? So if you want to model this situation, it means that if you make a connection which is a triple junction over here, you have to take into account that for a certain amount of road, actually, you're going with 2 trucks on the same road, but with 2 trucks. So that road actually should count for 2. And that is what I mean by multiplicity. Okay? So this you can do in higher dimension as well. It's a little bit more complicated, though. So let me give you a very simple example. So this is a 2-dimensional example. So you have this wire over here and this wire over here. And they have an orientation which I call negative. So this is like negatively oriented, and this is positively oriented. Okay, if you have this situation, an oriented surface which is spanning this wire is a piece of a catenoid. That is what is called a catenoid. So you have to imagine that here there is a surface of revolution which looks like a bend cone, right? So you have to imagine a cone or a piece of a cone which is connecting these 2 circles, and then you bend it a little bit, because by bending it a little bit, you're actually saving area. Okay? And this is allowed because these 2 disks, these 2 curves have opposite orientation. But if you have 2 curves which are oriented in the same way, it would be like having 2 factories in your problem before, and you don't want to connect a factory with another factory. You want actually to connect a factory with a city. Okay? So if you have 2 curves which have the same orientation, the solution of your Plateau problem would be to fill one curve with a disk, which you see over here, and to fill another curve with another disk. Okay? So this is a solution of what we call the oriented Plateau problem. So in the oriented Plateau problem, we cannot simply take arbitrary pieces of the curves and connecting them. They have to have a compatibility condition. Okay? As before, you had a compatibility condition between factories and cities. Now, although it looks a little bit weird, it's actually something which in nature happens. So if you are dipping 2 circles in soap water and you take them out, you actually find 2 disks Now, if you are connecting the two wires with a little tube and you pull it out, then in some situations you see the catenoid, in some situations you see this, in some other situations you actually see the two disks. So both situations occur in nature, in fact. Okay, so now this in higher dimension takes into account for orientation. Now do the following experiment. So you have your solution over here and your solution over here. In both situations, take your circles and slide them down until they touch. Okay? So in this situation, you have the upper disk, which is moving close to the lower disk. So when the two circles become coplanar, you find the outer disk and the superposition of the inner disk and the outer disk at a certain point. Okay? Here, the surface is empty on the top. So you only have the lateral surface. When you are sliding the top circle towards the lower circle, when you become coplanar, okay, your surface will degenerate into a corona. That is, into an inner disk without the outer disk. Okay? So now imagine that you have slide the circle until they become coplanar and look at them from above. Okay? If you look at them from above, you will see this. So on the left, you will see a circle with a hole. Okay? So the white hole means that your surface is only this corona. In the right, you will see the collapsing of the two disks. So the collapsing of the two disks gives you an outer disk, which is counted with multiplicity 1, and then a core. I mean, this is the black core that I have drawn in here. That core is the superposition of the two disks. Okay? You should count it twice. So the inner core has multiplicity 2. So now you have an interesting situation. So the boundary, so your wire is this disk and this disk over here. I mean, this circle and this circle, that is the boundary. And here also the boundary is this circle and this circle. In one case, we will say that the boundary points are one-sided, right? So the surface is always, on this boundary, the surface is always lying on this side. On this boundary, the surface is always lying on the other side. But when you are sitting at the boundary, you always see a surface on your right, maybe, or your left, depending on where you are, and you see nothing on your left. So these are one-sided boundary points. In this example, if you are sitting at this point, you are one-sided. So you see your surface on one side of yourself, and you see nothing on the other side. But if you are sitting at the boundary between the black region and the shaded region, you will see surface on both sides of you. Only on one side, you will see a surface counted twice. On the other side, you will see a surface counted once. Okay? So these points, we will call them two-sided. And what we conclude from these examples is that actually the oriented Plateau's problem admits minimizers which have two-sided boundaries. Okay? And this will be very relevant for what I'm going to tell you in a few slides. Okay, so what have mathematicians done then in this situation? Okay, so back in the 60s and 70s, through the major contributions of three mathematicians, so the Giorgi in Italy and Federer and Fleming in the United States, so these mathematicians funded the theory of integral currents. So what did they do? So they defined the most general surfaces with orientation, which have finite area and which have oriented boundary with finite area. Okay, so in our previous situations, we have a curve of finite length, which is bounding a minimizer. This minimizer is an oriented two-dimensional surface with finite area. Okay, so you could ask, what is the most general objects which I can define with this idea? So how rough can they be? How singular? And the answer is in this theory, which is called the theory of integral currents. Now, these general objects, on these general objects, they actually proved two theorems. So the first theorem is an existence theorem. So the theorem says the space of integral currents is closed and compact. So these are certain mathematical properties which ensure you one thing. For any reasonable boundary, oriented boundary, in a reasonable Riemannian ambient space, so in a reasonable geometry, there is always a solution of the oriented Plateau problem. So there is always a generalized surface, an oriented generalized surface, which is the absolute minimum of the area functional, which is therefore a candidate solution for your classical Plateau problem. So that's one theorem. Okay, the second theorem is more difficult to explain. So for mathematicians, the second theorem is saying that the space of integral currents is the variational relaxation of your initial problem. So what exactly does this theorem say? So this theorem says that although the space of surfaces that you have defined is slightly more general than the space of usual surfaces, it's the minimal generalization that you can use to prove that theorem. So it's true, you admitted surfaces which have a certain type of singularities, but you didn't get too much junk, okay? The least amount of junk and irregular surfaces that you can include in your theory to have a nice problem in the calculus of variations. So these are the two theorems which are fundamental. And for the experts, this is, I mean, here I'm just giving a poor man version of the compactness theorem, and here I'm giving a corollary or a poor man corollary of the deformation lemma, your famous theorems. Okay, now what happens? So you have general surfaces, and now you have a minimizer. You want to understand something better about the shape of this minimizer. So for instance, what is the type of singularities that might occur? Maybe they don't occur. I mean, maybe you minimize the area and you always find something regular. Okay, so the answer is yes. Actually, they always have, I mean, there are, in most situations, there might be singularities. So one interesting situation, and the best studied situation, is the so-called codimension 1 case. So what does it mean, codimension 1 case? This is very similar to the original Plateau problem. So your ambient space has one dimension more than your minimizer. So for instance, the Plateau problem is in the three-dimensional space, you look for two-dimensional surfaces which minimize the area. So the minimizer has dimension 2, the ambient geometry has dimension 3. So one less. So this is called codimension 1. Now in codimension 1, a famous example was given by by Bombieri, De Giorgi, and Giusti in 1970. Actually, the example was written down by Simons, and it's therefore called the Simons cone. And what these three famous mathematicians did, they proved that this cone, the cone actually has a very simple formula. So this formula gives you a 7-dimensional surface in the 8-dimensional space. It has a singularity in the origin, so when all the coordinates are equal to 0, you get the tip of the cone, if you want. And this object is actually a minimizer of the area. So what do I mean by a minimizer of the area? So this is an infinite cone. So you cut it with a very large sphere. When you cut it, you find the boundary. And your cone is the only way of continuing your boundary inside by minimizing the area. So there is no other minimizer. It's even the unique minimizer. Okay, and it has a singularity at the origin. So it's a 7-dimensional space, a 7-dimensional solution of the oriented Plateau problem in 8 dimensions, and it has a point singularity. Okay, even in higher codimension, actually you have singularities. You have many, even more. So Federer in 1979 gave an example of a 2-dimensional surface. So the surface is very low dimension, but it's in the 4-dimensional space. So the space is 2 dimensions more than the minimizer. This surface, you can write it in complex coordinates, and so in complex notation, this is the equation which is satisfied by the coordinates. So you see that you have one single equation, but these are complex numbers. So if you write the equation for the real part and the equation for the imaginary part, you actually get 2 equations. And 2 equations in 4 unknowns gives you 2 degrees of freedom. This should be a 2-dimensional surface in the 4-dimensional space. And it has, again, a singularity at the origin. Okay? Now, this is very nice, but of course, although the singularities exist, they are very small. So you could ask the next question, which is, okay, maybe there are singularities, but how large are these singularities? And the first very nice theorem, which was proved in the 1970s by the cumulated work of several people, starting with the Giorgi and then going on with Fleming, Almgren, Simons, and Federer, is that in codimension 1, this Simons cone is the first occurrence of a singularity. So the singularities can have dimension m, the dimension of the minimizer, minus 7. So if you have a 7-dimensional surface, you might have a singularity of dimension 0, a point. But if you have a 6-dimensional surface which minimizes the area in the 7-dimensional space, the singularity can have dimension only minus 1, and this means it has to be the empty set. So there are no singularities. You're actually smooth. Now, in the higher codimension, there's also another theorem that tells you, and this theorem is by Amran in 1980, it tells you that also the example of Federer is optimal. So in higher codimension, an m-dimensional minimizer has a singularity which has dimension at most m minus 2. So if you have a 2-dimensional surface, the singularity can only be 0-dimensional, so can only be some points. So it's very nice because it tells you that you have the examples and that you have also a full answer on how large the singularities could be. So the examples are the first or the easiest singularity examples that you can imagine. There's nothing more complicated than that. Okay, so now there are some issues with this though. Codimension 1 is well understood. So it's a theory, it's a theorem which is streamlined. It has a proof which is written in several textbooks. I mean, I can give you several references. It's a textbook for, well, advanced mathematics students, but it's a textbook anyway. I mean, you can learn it, for instance, in your master studies at the university. I mean, maybe if you're brave, even in your bachelor studies. Bachelor studies maybe to be, it's a little bit exaggerated, but in master studies for sure. There are several powerful generalizations, and it has actually been applied in several situations. I mean, it has been applied even to very famous problems in mathematical physics. So, for instance, the positive mass theorem in general relativity is proved by using this theorem. And it had a great influence of these ideas in the mathematical literature. So the ideas of the proof have been used in several places. Now, in higher codimension, the situation is completely different. So first of all, Amran's proof is scary. So it was, at the beginning, when he wrote it, 1,728 pages. It was never checked by anybody. It has not been published in a journal. It has been collected in a book, which is a very fat book of 1,000 pages, because the font is very, very tiny, and the pages are large. And it is available, but probably nobody has checked it. There were no generalizations up to some few years ago, and people were even scared to apply it. For instance, I mentioned the Gromov-Witten invariance, so there was a famous mathematician who wanted to apply it, but of course you're scary of applying a proof of 1,700 pages that nobody has checked. So what happens if actually the proof is wrong? And you want actually to infer some consequences of the proof. Okay, so Fabio was mentioning that one of my works has been, in the last years, to actually produce a shorter proof. So together with my former PhD student, Emanuele Spadaro, from 2009 to 2015, we have produced actually a shorter proof in 5 papers, but they are papers of normal size. And this has actually some added values, so there are some generalizations. I don't want to go through all of them. I mean, you see somehow the people who were involved, and there are a few other that are coming. I mean, if I had more time, I would explain you what are these generalizations over here, but let me not go over this. Let me tell you that what is interesting is that by building upon this work, we can actually tackle new open questions. So in particular, one very nice question actually appears at the end of the book of Almgren. So at the very end of the book, he asks the following open problem. So it's a very natural geometric problem. So assume that you have your boundary, and that your boundary has only multiplicity 1, so it's a classical surface, and it consists of one piece. So in mathematics, we say it's a connected surface. Now the question is, the minimizer, does it consist of also one single piece, or does it consist of maybe more pieces? Now, intuitively, what you would believe is that, yes, it should consist of a single piece. And the idea would be something like this, that every regular piece should actually touch the boundary. And since the boundary is one single piece, once it touches the boundary, it actually touches the whole boundary. Now, your piece reasonably will have the boundary. I mean, if your piece has multiplicity 2, your boundary will be taken with multiplicity 2. Okay? Now, if you have several pieces with multiplicity 2, 3, 4, whatever, the total area is the sum of the areas of all pieces counted with the respective multiplicity. But one single piece counted with multiplicity 1 is already bounding your boundary. So, of course, that one has much less area than the sum of all of them. And that is a minimizer, not the sum of all of them. So it should be of one single piece. Now, why does he ask actually this question? Because you could say, okay, so this proof is convincing, but if you want to formalize, there is one problem. So for instance, one thing which looks very simple is the following thing over here. So I'm just saying regular pieces of the minimizer with different multiplicities should be totally separated. So they should be really things which are far apart. That's not obvious. So if you remember the example of the configuration of the triple junction, okay? So here you have a triple junction. Of course, when you have a triple junction, I told you here you have the two tracks, and they are bifurcating into one track over here and one track over there. So here you have a piece with multiplicity 1, here you have a piece with multiplicity 1, and here you have a piece with multiplicity 2. But there are two tracks coming and two tracks exiting. So this point over here is not a boundary point. So the idea that each single piece should touch the boundary and should touch only the boundary and bound that particular boundary and be completely separated from the other pieces is not correct. Actually, the multiplicities could jump around singularities. So that might happen. Now, although that is true, so you see something like this. So here you have a one-dimensional example, and you have a point singularity. So the reality is that the singularities can jump. I mean, the multiplicities can jump, but they can jump only if the singularity is sufficiently large. If you are looking at lines, the multiplicities can jump at points. But if you are looking at surfaces, the multiplicity can only jump along curves. So your singularity where your multiplicity is jumping should be at least of dimension 1 less the dimension of your surface. Okay? So that is what we learned. Multiplicities can jump at interior singularities, but the singularities must be large. In an m-dimensional surface, the multiplicity can jump only along m-1 dimensional singularities. But Almgren told you that the singularities in the interior have dimension at most m-2. So there are not enough singularities in the interior to allow to the multiplicity to jump. So this point A, that is that every single regular piece has its own multiplicity and it's kind of separated from the other pieces, is essentially correct. So they can join on, for instance, two-dimensional pieces can join on points, but they cannot join on lines, unless the lines are actually boundary lines. So that tells you that the first part of the intuitive proof is correct. Now, what about the other two parts? So what about my claims at the boundary? So I have my regular pieces, which are separated, but I told you they are regular inside. I didn't tell you anything on how they touch the boundary, right? So far, I only cared about interior singularities or interior regular points, but never about boundary regular points. Okay, so this is a simple remark. So the program, the proof would be correct if the boundary is taken in a regular way. So what do I understand by a regular way? The sheet is coming, and it stops nicely at this curve. Okay? It doesn't make some sort of fractal construction towards this curve. It's not kind of bending crazily or doing things like that. Now, there's a very nice theorem. This was a fundamental result in the 1980s, and it actually tells you in codimension 1, I mean in the situation which was very understood in the interior, actually there are no singular points at the boundary. Okay? So if the boundary is nice, the surface, the minimizer, arrives at the boundary nicely. There can be interior singular points. But then this means the interior singular points have to be at a certain distance from the boundary. You cannot have singular points which are getting closer and closer to the boundary, for instance. This was a fantastic result, and it tells you that the answer to Almgren's question is yes, in the case of hypersurfaces. But unfortunately, the theorem is false in higher codimension. So even for the mathematicians, even real analytic curves in the four-dimensional space can actually have boundary singularities. So even the best behaved curves can have boundary singularities for the oriented Plateau problem. And therefore, we cannot hope to prove the theorem of Harden-Simon. Okay, now there's a good news. So there is a simple remark that you can do by using the theory which exists up to now. I mean, it's a proof of half a page. So it's a remark that I've made together with these friends of mine, Guido de Philippis, Jonas Hirsch, and Annelids this year. And the remark is that actually you don't need the boundary to be completely regular. You need one single regular point at the boundary. So one place where the surface is reasonable at your boundary, and then the answer to Almgren's question is positive. So, problem. Although it looks very strange, up to now, the situation of the literature is that, in general, you don't know that there is a singular point at the boundary where your minimizer is reasonable. It might actually be that all the boundary consists of singularities. You have kind of a scary fractal behavior at all the boundary points. So which is kind of completely opposite to what we know in the interior, where we know that the singularities are actually few. Okay, so now remember the following, because this is going to be very relevant for the next 10 minutes. So in this business, boundary points might be two-sided and might be one-sided. And actually what happens is that the two-sided situation is what is creating really a lot of problems. And that is because it was known since the PhD thesis of another famous mathematician, Bill Allard, that if you can exclude two-sided boundary points, so if at every point of your boundary, the surface is only lying either on your right or on your left, but it cannot be on both sides, then actually that point or the whole boundary has to be regular. So now this seems a nasty, strong assumption, but it's not. So there are a lot of situations where you can actually ensure that there are no two-sided points a priori. So let me give you an example. So assume, for instance, you are in 3 dimensions, and your curve is lying on a sphere. So your curve is lying on a convex surface. Okay? So there is something which is called maximum principle or barrier argument, which guarantees that your minimizer has to be only on this side. I mean, the minimizer cannot go outside of the sphere. It has to be only on the inside of the sphere. And that guarantees actually that you are one-sided. And so it guarantees by Allard's theorem that you're actually regular. Okay? So as I said, the core of the argument is that the convex surface acts as a barrier. And it tells you right away, if you're sitting at the point of the boundary, you just look at the point in such a way that the outside of the sphere is lying on the left, and the inside of the sphere is lying on the right. And then the maximum principle, the barrier argument, actually guarantees there's no surface on this side. It has to be in here. So the surface is never going to be two-sided. I mean, it sounds easy, actually. It's part of the PhD thesis of Bill. So it's not an easy theorem. Anyway. Now, in our standard Euclidean space, you can actually use this idea to find at least some boundary point. I mean, say that I give you a curve, okay? I sit, say, in the middle of the curve somewhere, say in the origin. The curve is around me. I can look at the most distant point. At the most distant point, there is a sphere which is touching the curve in such a way that the curve is all on this side of the sphere. And that sphere actually acts as a barrier, and it tells me that that point can only be one-sided. And if that point can only be one-sided, Allard's theorem actually tells me that that point is regular. So here is an illustration. I mean, I was trying to draw this. I mean, it's the old surface, see? I mean, this is where the curve should lie if it were on the sphere. And this is a piece of the curve which is actually getting inside. I mean, it's a kind of spike. Okay, Allard's theorem would tell you, I don't know anything about this spike. In this spike, actually, the surface might be irregular. But along these points, which are lying on the sphere, and such that the curve is all lying on the other side, on these points, actually, I'm regular. So now this means in our situation, in the classical space, in the classical Euclidean space, I know that there is at least one boundary regular point by Allard's theorem. Okay. So in the standard Euclidean space, there is always an outermost point, and Allard's theorem actually guarantees that that point is a boundary regular point. That is the upshot. However, you need a concept of most distant point. You need a concept of convex surface, which is kind of enclosing your object. And that is only available in some special geometries. So in the standard space, that is possible. But if you have a general geometry, it is not. And you might wonder how likely it is that your geometry allows for these barriers. And actually, the answer is that it's very unlikely. Usually, you don't have these barriers. As soon as you have, for instance, an ambient manifold which is not infinite, I mean an ambient manifold which is bounded and closed, like it would be a normal sphere, for instance, then you cannot apply this argument. And you are left with the problem that you don't know whether there are boundary regular points at all. Okay? So we have been working at this problem since 4 years, I think. 5 years, Annelids is suggesting. We are writing what Annelids calls our own personal version of Tolstoy War and Peace, because it's a pretty long work. But it's all written, we are proofreading it, and it actually proves the following. So in any situation, in any ambient geometry, for any dimension and codimension, the regular points at the boundary are dense. It's a dense, relatively open set. That's what we would say in mathematics. In layman words, that means the singularities, the boundary irregular points, can only be a scattered set. So it can only occur in relatively few points, relatively few in a topological sense. So it's a kind of powder which is scattered around. It doesn't have any bulk. And so since it does not have any bulk, it tells you there are a lot of regular points. At least there is one, but there are actually many. And you have to notice that it tells you something interesting even in the old case, even in the Euclidean case. So Allard, in this situation, was telling you these points are regular, and here, who knows? Our theorem is telling you here there might be singular points, but they are few. So even in here, in the portion of the curve to which I cannot apply Allard's argument, I will find a lot of regular points. So it's giving you actually an interesting information even in that case. Okay, that is the theorem. Now, another thing which you should actually be aware of is that we found out that the boundary regularity is much more trickier than it's much more tricky than the interior regularity. So if you have two-dimensional surfaces, I told you that the singularity can only have dimension 0, but I can actually do something much stronger. I can tell you if there is a singular point, the singular point is there isolated. All around that singular point, everything is regular. Now, this is a theorem which was claimed by Chang in 1988, and in fact, he provided a correct proof, but a correct proof which was missing one ingredient. Okay, so if you literally read the paper of Chang, it would tell you. Okay, so here there's 80 pages proof, but you should read the 1,700 pages of Almgren, redo it in a way, and after you have redone it in a way, you start with my proof and I complete. Okay, so together with Emanuele Spadaro and Lucas Polaor, we can actually build these missing pieces by modifying our proof of Almgren's theorem instead of going through the 1,700 pages. Okay, so we have provided somehow a written confirmation that this missing piece actually can be proved. Okay, the situation is different at the boundary. So at the boundary, I can have singular points, which are not isolated. I mean, singular points, which are the limit of a sequence of singular points. So I cannot claim that around that singular point there is a neighborhood where all the other guys around, they are regular. Okay, so I have infinitely many singular points which are converging to it. So in the interior, I have locally only finitely many singularities, because I cannot converge with a singularity towards a singularity. At the boundary, this is false, which actually tells you that our theorem is possibly harder than the one at the interior. So there's something more mysterious going on that we have not completely understood. Okay, so now this, since I have some fellows actually from partial differential equations here, so the last 4 slides are for them. Okay, so if you are just not a mathematician, not yet a professional mathematician, and you're not understanding these slides, don't worry. So I'm not saying you should sort of switch off the brain because maybe you have enough calculus to understand something, but I mean, this is more for experts because they have been sitting here for 45 minutes listening to me. I owe them at least some mathematics, some formulas. Okay, so I cannot, of course, give you an idea of the proof of this because it's a very complicated thing, but I can give you a very nice, simple consequence for partial differential equations, which is really cute. Okay, so let me state something which is an exercise, essentially. Okay, well, for a class in partial differential equations, it's certainly an exercise. So consider an harmonic function on some domain, some open domain. Okay, so you have a function which solves Laplace u equals 0. Assume the origin is in your domain, and assume your function vanishes at the origin. So it's a 0. The origin is a 0 of u. Now, assume the origin is actually a 0 of infinite order. So the function u of x vanishing faster than any polynomial, than any monomial at the point 0. Okay, then the exercise is to prove that u vanishes identically. And of course, a good student would solve it immediately. I mean, a good student would tell you, okay, so the harmonic function is real analytic. If it is real analytic in a neighborhood of 0, it has a power series expansion. If the power series has one non-trivial polynomial, okay, then it's vanishing at that order. If it vanishes at all order, that means that all polynomial in the power series expansion is trivial, and therefore the power series expansion is identically 0. And in the neighborhood of your point, you have to be 0. Of course, you don't have to vanish on the whole omega because maybe omega is disconnected. Okay? So that's nice, but it's a complicated proof because it has to go through the theorem in which you prove that an harmonic function is real analytic, which is non-trivial. So there's actually a solution which only uses calculus 2. I mean, only uses calculus 2 without any regularity, any PDE. Okay, and the solution is the following, and in fact, it's a byproduct of Almgren's theorem. So look at this function. So this function is a function of the radius r. So you integrate over the ball the Dirichlet energy, and you multiply by r, and you integrate over the sphere modulus of u squared. Okay, this function, as long as it is defined, I mean, you might have problems defining it because in principle, you have not yet proven that your harmonic function cannot vanish on the boundary, but okay, let's assume that. It's easy to prove. So this function is actually monotone non-increasing, okay? In particular, since it is monotone non-increasing, you can take the limit as r goes to 0. And the limit as r goes to 0 is finite. Now, it's not that difficult. I mean, it's a pretty tough exercise, but the solution is very easy. So it's a perfect exercise for calculus 2. I mean, finding a proof that this one is monotone is not easy. But once I show you the proof is only a simple computation. I mean, it's a half a page computation. Now, the very nice observation, which is also elementary, is that this number, which is the limit, is a positive integer, and it is the degree of the first non-trivial polynomial in the Taylor expansion. I mean, with one caveat. You don't need to know that the function is real analytic to show that the function cannot vanish faster than a polynomial with that degree. You can prove it in an elementary way. Okay, and this is, I mean, it's a very simple, it's an absolutely beautiful piece of work, and this very simple first building block is the starting point for Almgren's 1,700 pages proof. But it's just simple observations, half a page computation. Okay, now there's something similar in our work at the boundary. So I modify it in the following way. I give you a boundary point, and I assume that the function not only is an harmonic function, but it also is 0 at the boundary, okay? Now, assume, of course, that your boundary is not bounded, it's not because otherwise the harmonic function would be identically 0, okay? But imagine your harmonic function is defined on the upper half plane, and it's vanishing on a line. Okay? Now, the theorem is still true if the function vanishes at infinite order at this point, okay, then it is identically 0 at that point. And if you have a function which is harmonic on the upper half plane, of course, your smart student would give the following proof. You make Schwarz reflection, and you produce an harmonic function on the whole plane, which has 0 of infinite order at that point, okay? But now it's more tricky because if your boundary omega is not flat, you cannot use Schwarz reflection principle. Or you can try to use it, but then you have to make the coefficients of the PDE different. You have to use Schauder theory. I'm not saying you cannot modify that proof so that it works, but it's going to be more complicated. Okay? And now I give you a slick proof. And the slick proof is a consequence of our theorem, although it's a consequence of our theorem that we realized after 5 years of work. I mean, we had written all the proof, and then we have realized this theorem, which is a very nice computation. So the theorem tells you, modify your frequency function of Almgren, so your function I of r, in the following way. So here you have the integral of a test function phi. I will tell you what it is. And here there is something which looks like a distance from 0. Okay? So this is what you have in the numerator. And here is what you have actually at the denominator. Now, provided you have the following properties. So provided phi is decreasing, so phi prime is less or equal than 0. It's a function of one real variable because this function d is like a distance function. Provided this distance function has the property that the gradient of d is tangent to the boundary, and provided that this distance function behaves like modulus of x asymptotically around 0. I mean, I could be precise about this. I mean, for the experts, it needs the function, the first derivative and the second derivative, to have the same asymptotic decay or blow up of modulus of the corresponding derivatives of modulus of x. Okay? You can perturb it by a higher power. Okay? Provided you have these three properties, then that function is actually monotone. And that function can substitute Almgren's function in the proof of the exercise, in the solution of the exercise. And producing three functions, producing two functions, so phi and d, with these three properties, is a very simple calculus exercise, as long as your boundary is sufficiently regular. So you have to produce a kind of distorted distance function. Okay, so the nice observation is that actually this is a strict generalization of Almgren's theorem because it works in the interior. And Almgren's function is a particular case. So Almgren's function is the particular case in which phi of x is the indicator function of the ball of radius 1. Then this bulk integral is literally the same integral as we saw before, and this integral down degenerates to a surface integral. Okay? And in Almgren's frequency function, the distance x is exactly modulus of x. Okay, so there is no asymptotics. It's exactly the precise modulus of x. And then you recover actually Almgren's function. Okay, and with this, thank you very much for your attention.